Before we jump into an in-depth discussion of how to solve this equation, it's helpful to try to build up a little physical intuition about what it is actually telling us. The first thing to notice is that this term that multiplies rho Lm of r definitely just looks like some kind of a potential function, some V effective of r. It's known as the effective potential. And then, if I'd like, I can make a sketch of the one-dimensional Schrodinger equation that I need to solve. So let's try to sketch this here. So I can sketch, for instance, this effective potential in which I have to solve what looks like exactly a one-dimensional Schrodinger equation. It's a function now not of x, of course, but it's a function of r. And this effective potential, you will notice when r becomes very large, for example, we should always check the infinity and zero cases. When r becomes very large, this term will become much smaller because it's divided by r squared. And what I have then is this negative 1 over r piece. So it's going to approach 0 from down below. Maybe I'll make it like more 0 here, and it starts to drop down. So this is going to be something that goes like minus 1 over r for my potential there. As r heads towards 0, my potential, notice, is then dominated by the first positive term, which heads up towards infinity as r heads to 0. And the behavior on this piece is then something like 1 over r squared. And the overall function, of course, has to be a continuous function, so it somehow has to come down, it somehow then has to come down below my axis first, so that then it can curve back up and join with the rest of my solution. So that's the general appearance. I want to make this a little better, make it look a little steeper on this side, something like this. That's the general appearance of this effective potential. There's one other little subtlety, but otherwise this looks just like a one-dimensional Schrodinger equation. That subtlety is that the radius r only exists in spherical coordinates between 0 and infinity. It has no negative values. So all of the negative portions of r are completely forbidden to any wave function. So there is no behavior here for r less than 0. Now, we might ask, well, where is this effective potential coming from? This second piece, of course, is the actual potential. This is the Coulomb potential. And if we did something else like a harmonic oscillator, this would just be something like 1/2 kx squared, right? This first piece comes from all of our angular motion. And you can see it's really the angular momentum squared divided by twice mr squared. This is really the square of the angular momentum, right, divided by twice I. It's the rotational kinetic energy in the system. And what it's doing, right, is it's saying if I have some angular momentum, it's getting very, very hard, actually, for me to bring my particle down towards the center. And that's something that should be very familiar to us, right? That's like when we're in a rotational system, there's this effective centrifugal force, it's called, which actually tries to push us away from the center. It makes it hard to pull things in. And because of that, that's the name this is often given. This is called the centrifugal or centrifugal potential. And we've derived this thing rigorously. It's not like some fictitious term or fictitious force that it's coming from. It's just it gives us a mental picture of its origin and where it comes from. Finally, before we really think about doing deep mathematics on our equation, it's nice to try to use our sketching skills to get an idea of how my solutions will behave. And the first thing I think that you will notice is that if I want to find bound states, right, they have to be bound in a one-dimensional system. So I need my energy will have to actually be less than 0 to be able to bound the state to keep it from going all the way off to infinity. Because after all, we are right now just solving the same equation we've been solving for quite some time now. Now, we can sketch our solution, though, if our energy is like this, because you will notice we have different regions. This first region here, before my dashed line, this is where the potential becomes higher than my energy. This is a forbidden region for my wave function. In here, the energy exceeds the potential curve, so this is an allowed region, and then at this point, I switch back into a forbidden region. So I can even sketch my wave functions then, right? My wave function will have to in this forbidden region be always curving away from the axis. So it'll have some kind of general appearance maybe like so. Then when I'm in this classically allowed region, it can oscillate. So I don't know, it might have a couple of oscillations like thus. And then finally, as it moves into this forbidden region, we know it has to again undergo some, now it has to curve away from the axis. And as we get far away from the origin, notice the potential is just going to nearly a constant. It's going to nearly zero. So out here I can be pretty sure I'm going to have something that looks like exponentially decaying type solutions. So this curve then is my effective potential. This is the type of solutions that I'm expecting for my radial functions rho sub Lm of r. So that gives us kind of an intuitive feel for our solutions. Our job now really is to start the hard work of solving this equation in its full glory.